So that problem number 6 of section 5.3 is very similar to this one. And it was just not that much hard. It could be really harder, but it's just somehow related to this situation that we are in right now. And it was really interesting problem. I don't know who tried it. Have you tried, or did you think about what's going on?
Yeah, I mean, I did, and there were a couple different things that I tried, you know, and so it's just kind of it's
It's a nice one,
what
right?
what I learned is it matters how you set up.
The matrix.
Yeah, if it's about like being able to set that up properly. So I can just pull up the problem. My work is scanned in. I can pull up the work on the
So let's just go. I hope everyone is just here has that problem somehow on your mind or in front of you. So just let's read the problem first. Where is it?
Okay, let me go there. It's, what is it, 3?
Looking number 6. Okay.
Yeah, number 6.
This is just very similar to the situation that we are in. It's just the statistic shows 30% of the patients are. So if I just.
So yeah, it's the question has to do with the fact that you have 4 different states, right? You have a patient who's recovers. You have a patient who is ambulatory. You have a patient who is bedridden, and you have a patient who expires, right? And your Markov matrix, right? Your what is it? Your probability matrix, right?
Mm-hmm.
Transition matrix. The columns tell you what state that you're in. So my first column is I'm a healthy patient, as in I'm not admitted to the hospital, right? That's a recovered state. The next column needs to be the, what is it? The ambulatory. The third column will be the bedridden, and the fourth column is going to be expired. And the rows
okay.
The rows will tell me the probability of moving from the column that I'm in to the state that the row is in. So in the confusion that I had is that, is that even the right way to set it up, right? Because it should be a square matrix, and there are 4 conditions that we're coming for. But if that's the way we set it up, then it's like, how I don't know how many healthy people are getting, are becoming bedridden or becoming ambulatory, or ambulatory. Now I am given that initial probability vector, and at first I was like, okay, do I only consider the cases? Do I not consider new people getting admitted to the hospital? And in that case,
okay, so then 30% are the ambulatory, the 7%, 70% are the bedridden, and then this is just what. Sorry. We still okay. So we will still read through the problem and fill out the column. So as you said, I'm going with the rows. So it says 60%. Where is the first one? So 30%, 70% are bedridden, and then 60% of 60% of ambulatory patients have recovered. 60% of ambulatory has recovered. So this is just like this. And then next one. 20 remain ambulatory, and 20 became bedridden. 20 became bedridden. And then after same amount of time, 10% of patient has recovered. 10% has recovered. And then I think for this column, I'm done almost, right? So that's my first sentence. Does it make sense the way that I'm filling the column? So 60 plus 40 is 0 left. So no one dead.
So the first column is going to be ambulatory, right?
I don't go by column. I go by rows.
Okay, so the first row, well, yeah, but the
Okay,
like,
so let's just go back to read the sentence again. So the sentence says what it says. The sentence says after a month, 60% of ambulatory patients have recovered. Okay, so 60%
sure.
have recovered. So that's why I have it here. And then
Yeah, but I mean that means that this column is ambulatory. The first column is ambulatory because columns and rows are both associated. Yeah.
So yeah. So then 20% remain ambulatory. So that is just that 20% right there. And then another 20% become bedridden. So this is another 20%. So that was the first sentence. And after same amount of the time, 10%. So I was here, bedridden. 10%, sorry, of the bedridden. So this was ambulatory, that was bedridden. And then has recovered. I wrote it, that one. What's the next one? 20 had become the ambulatory, and 50% remain bedridden. Is that true?
Yeah, yeah.
So what is left?
Is and it says that 20% expire. So.
Oh yeah, so you just add up 100%, and then yeah, the last one, it didn't say anything, right? So determine the percentage of the patient who have recovered.
Yeah, and so
yeah.
I mean, you know how many patients are recovering, you know, but it's like
recover and death, right? So this is
right.
going to be so means they are not here, all recovered and they are not here. So this is means they are not here, so they did. So it's just really one chance of 100% to recovered and one chance of 100% to death. Okay.
Yeah, that's the first thing that I tried, and then I multiplied by the vector right here, you know. And I just, you know, both ways that I tried it, I wasn't able to figure out what percentage of patients eventually recover and what percentage of patients eventually die.
Can you explain one more time how you got the recovered and the dead columns for that? The 001, 00001.
So this is the column that all of them recover. So right, and this is the column that all of them dead, right? So then that means they don't have ambulatory, they don't have bedridden, so they just recovered from recovered, and then that's just 100%. And the death means nothing happened for all of them, so it's just really right away they die.
Yeah, it's assuming that basically you don't have any measure of how many patients that are recovered end up becoming bedridden.
So then the lambdas that I could get after determinant of a minus lambda I set it equals 0 was 1, 1, and 0.6 and 0.1. Obviously, it's easier to do by calculator, right? So this is
I mean, yeah, but that's what I got.
This is just the lambdas that I got, and then corresponding to the lambda equals 1, I got, seems I have 2 of them. 0, 0, 1, 0. That was just for the first one. And eigenvalue for lambda equals 1 has 2 free variables. So this is what I got.
Yeah,
And
and that makes sense because, you know, though, no matter how many times you apply that matrix, your recovered patients aren't going to be changing and your expired patients aren't going to be changing.
So then this is really diagonalizable. So means I have enough, eigenvectors, huh? So these are the eigenvectors. So these are the numbers that I got. Obviously, any scalar multiplication of those is fine, right? So you might get just a scalar negative of those. So still is fine. So in this case, my diagonal matrix, if I just want to set them in the same order, I just put it 1, 1 first, and then put the 6 next, and then put the 1 next. So this is my diagonal matrix, and everything else is 0. And then for the Q, with the same order, I have to first put the first one, which is 0, 0, 1, 0. This is 0, 0, 0, 1. This is just negative 1, negative 2, 2, 1. And this is 18, negative 9, negative 11, and then 2. Okay. And then that's it. That's just the process. So what I've done is just really follow what happens. So you multiply infinite many times to the cases of what is 30% ambulatory, what was the 70%? I forgot, what was the 70% for? Recovery, right? So, no, bedridden. And then no one recover and no one, because it's 100%, so it's nothing from the dead and recovered. Okay, so this is going to be one we have learned, Q, D, and then Q inverse, and then multiply by whatever is your vector, given vector. Okay, so that's just my diagonal matrix of 1, 1, because this is just rising to the infinite many, right? So since this is just really a infinite many of diagonal matrix, as we know, when we have a number which is small, rise it to the infinity means that's just 0. And then if we have something which is too small, rise it to infinity, that is 0. So this two, if I can just give some room.
Yep.
So that gives me 1, that gives me 0, and that gives me 0. Is that fine? So from here to here is when you write a to the infinity, which means Q, D to the infinity, then Q inverse, right?
Yep.
And then you multiply by that thing. The numbers that I got is just in the solution. I will post it for you. So the numbers that I got is just like this after multiplication. Fine? Does it make sense? So that should be 0% of what was my first one.
Yeah.
Ambulatory, 0% of bedridden, and this much people recover, and that's just really, and that makes sense. Yeah. So you have, after a few months, after a few whatever time you have, so the either people get just really released from the hospital, or they die, right? So they don't stay bedridden, they don't stay ambulatory. So you must get 0 on the top too. If not, that doesn't make sense, because no one stay there forever. And then this is either they release from the hospital, or you just they die.
Okay. Yeah. I mean, I just couldn't get that last step. I don't. One thing is, I set up my recovered column, or my.
But yeah, that makes sense right now.
First, so maybe I'd set it up this way next time. Like you set the both at the.
You mean your rows and columns are the other way, huh?
Yeah, and maybe I just got confused or something like that.
I think it works the other way too.
Yeah, I could have gotten the wrong eigenvectors.
Yeah. No, the other way I believe is fine too. So you can just, but that's just really, as I said, nowadays it makes a lot of sense when you do. And then I don't mind, what do we call it, this Markov chain, but that's not really that much complicated. It's similar to think that we can do it, right? So we can do it because we can do, I mean, we could do it, this type of problem in previous course. So which is a 2 by 2. So that's just really not that much complicated. Okay.
Thank you so much.
You're welcome. Any other question to discuss here? As I said, the plan for today, so I have to, after your class, I have to post the solution. I'm sorry, first solutions, I don't remember how many of them I didn't. So I think 2 assignments and the last group work and yeah, that's it. So this is the first thing that I will post right after your class, and then probably we don't have that much to do today. Is just really give you some introduction and finishing what we haven't had from the last class. I don't want to leave anything empty here. I don't know, have you tried this problem or not? Then after just your class, you will get that list of problems, 10 problems, which is just really about 2 days to finish it. So be relaxed. It's just really, you will have all your resources. You can discuss with your friends. And it's just really how you write for me. Okay, so be careful about write the details for me. I always say, don't think I know magic. I don't know magic. So I don't know how you thinking when you are writing something. So as much as detail you can write. If you're using theorem, you can say I've used theorem 2.14. So that's not the right way to write. So you have to mention because these assumptions are true. So that's just a conclusion. So you just please write the details as much as you can, and you have enough time, I believe, to just do those details for me. And if you have had any question, you must email me, and I can just email back to entire class. So that's just a question. This is just a concern, and that's probably it's typo. I don't think so. I hope it's not nothing. But if it's just really something weird, email me, please. Any question or concern about the test? When is there is no in-class one. No, there's no in-class one. That whatever you do for this test is 100% of your midterm number 2. Any other question? You're welcome. Okay. As I said, we have to just complete this problem. I don't know whether you have done it or not. And then I have one more thing, which is just something to prove one more time. This is 1-to-1, and that's it. Okay, so this is, and then in short introduction to what is next. So if it's not diagonalizable, what's the next strategy to do it? Okay. So this is again something that we've seen it in previous course, and somehow if we just go and do the method that we have learned at the end of what is the chapter, I think was just 11 somewhere. So you can just directly get the eigenvalues and just solve this system of equation. But before learning of that, so it was just really another method which using this what is it fact that I have written right over here in the right side. Okay, so I just want to work with numbers, right? So I just want to finish this problem and just see what happens. So as you see on the right side, the goal is to get the W's first, and then this is the W's first, and then when you just get the W's, you can just go and find the V's, which is your really X and Y's. Okay, so this format of what is it, V prime equals A times V, which is on right side, is right over here. So then I have to get what is the diagonal matrix, and then I have to get what are my eigenvectors to make these two Q's, and then I have to multiply by the V, and then in order to get the W's, I need to make it in this form. Okay, so that's just what the process is with the numbers. Okay, so the right side is just the process with the numbers, and then first step for me is get the D, or diagonal matrix for this one. Okay, so I have to solve for V. That's a goal. So what is diagonalize A? So this is going to be determinant of, I hope I have enough room, determinant of A minus lambda I, and then that gives me 8 minus point, oops, A minus lambda, 8 minus lambda, that is 10, and that is minus 5, and that is minus 7 minus lambda, and then determinant set it equals 0. So then whatever I have is 8 minus lambda times minus 7 minus lambda plus 50 equals 0. So then I have lambda square minus lambda minus 6 equals 0. So the factors are negative 6, so it's minus 3, and then it is plus 2, right? So that gives me lambda plus 2. So then I have to get, one is lambda equals 3, the other one is lambda equals negative 2. So for lambda equals 3, so this is just really algebra. I wish I have had it written. I don't know why I didn't. So this is just 5, 10, negative 5, negative 10. At least is a good practice, right? So I think you have 2 or 3 of them in the test to do these details. I mean, computational problems that you have to, can I make this one tiny? No. Negative 2, and then this is going to be null space for 10, 10, and then negative 5, negative 5. Is that fine by now? This is just really the algebra behind of this. So that gives me the Q has to be, what is it? The first one that I got was 2, negative 1. The second one I got is 1, negative 1. The diagonal matrix, scroll down, we can see the questions. Yep. That's the differential equation. 3, 0, 0, negative 2, then Q inverse. You know, these are all posted online, right? So this is just really on top of the page in the files folder. As I have finished this one, I will just really update the new version because that was just really blank. Am I good to move on? Okay. So then what was the original? It was V prime equals A times V, and then we just got V prime, and this is what we know about the diagonal. So it's Q, D, and then Q inverse replaced by A, and then I have V, right? So that means the V prime has to be equal by can I multiply? So let's just use different color. So can I multiply by left multiplication by what? So I just multiply left multiplication by a Q inverse because I want to cancel it out. So that gives me Q inverse first, and then V prime equals, then I have Q inverse, then I have Q, and then I have D, and then I have Q, and sorry, Q inverse, and then I have the V. Okay, so this was original one, but these two cancel out, so then it gives me what I wrote on right side. So it's just Q inverse V prime is D times Q inverse times V. And the process that we have had was just really called this one to be W. So this one is called to be dW. Okay. So then this one is called to be W prime. Right. So that's just what it is. And that's what we can solve it easier. So the whole goal is to make it somehow that you can do it. If we get W, we have the V. Okay. So then W prime is going to be D times W, and W prime is going to be 3, 0, negative 2 times the W, and that gives you W1 prime, W2 prime. It's just really simple differential equation that we can do by integration, right? W1 and W2. And that's what the differential equation is. W1 prime equals 3 times of W1. W2 prime equals minus 2 times of W2. Okay. So so what? I have W, oops. What happened? Okay. Then I have W1 prime divided by W1 equals 3, which if I integrate both sides, that gives me W1. I need to write more details, okay. Is that fine, or do I need to write more details? Because that's just really simple differential equation. Can I write this W1 equals, oops, W1 equals constant e to the 3t. Do you remember this one? Should I write more detail for this one? W2 prime divided by W2 equals negative 2. If you integrate both sides, W2 is some constant. So I will call this one C1. This is C2 e to the negative 2t. Is it fine? One more time. If I integrate both sides, so then that's a natural log equals 3t. So then you have to e both sides, then that's just what happened. Okay. So this is my W1 and W2. And then if I have W's, as you see on here, we will have the V's. So if I have the W's, so then we will have the V's. I think I need to make it same size. Otherwise, okay. It's too big. Okay. So then, as we had right over here, or just here, let me just highlight it. That's just what the relation between W and Q, so and V is. So then, your V has to be what is it? Q times W. So your V's are Q, which is 2 negative 1, and then 1 negative 1 times the W's that you got, which are C1 e to the 3t, C2 e to the 2t. So then you distribute, and that gives you whatever your V is. 2C1 e to the 3t plus C2 e to the, was negative 2t, or negative 2t. So that's just really what I'm doing. This multiply by this, right? So that gives me negative C1 e to the 3t plus minus C2 e to the negative 2t. Okay, so that's just x of t this is y of t, right? So this is x of t and this is y of t. And that's the solution. Okay. And again, on right side, I just gave you the whole idea of that. We have had it in previous course. So this column on right side is showing you why we are doing in this way, the idea from the other course. And that's just really the calculation. Any question here? Any question here? Okay. I think we have discussed about this one. We have any question for this one? So this is the number 3. Was number 3 part of your homework or no? To show this is isomorphism. So let me erase here and show that is isomorphism. Okay, so this is, I can add this one later, huh? Yeah, I will add this one again. This is, I will add it later. So let's just prove this one. That's just what it says. You have to move from matrix transformation is moving from the n by n matrices to n by n matrices. And what it does is just really corresponding by each A gives you similar matrix, right? So that's what we call similar matrix. So somewhere, yeah. So on here it says behind B oops. B is invertible. Okay, so that's why this makes sense, and that's why that's really being similar. Okay, so corresponding by each A, it gives you one similar matrix. So this is just really the process of showing something is isomorphism. If the size of both sides is the same, that's just really enough to show one of them. Either is 1-to-1 or onto. Okay, so since the dimension of V equals dimension of the W, so it's enough to show one of them, right? So for me, I think 1-to-1 is easier, but it doesn't matter. So to show is 1-to-1 or onto to prove isomorphism. Okay, to prove isomorphism. That we have just really discussed about it. Be careful if the dimensions is the same. It doesn't mean it's already 1-to-1 and onto is already isomorphism. So you have to show either 1-to-1 and onto, then you can stop. So for this one, this is a transformation. So first of all, this what is the transformation preserves the addition, which means B inverse A1 plus A2 times B. I can just distribute to the B inverse A plus, sorry, B plus B inverse A sub 2 B. So that's just really simply distribute from right side and left side. So you can do it in 2 different steps. One, distribute B1 to the left side and then distribute B to the right side. So that gives you, yes, that preserves the addition. That is preserving the addition. So that's number 1. Number 2, it preserves the scalar multiplication. So if you have a constant times this, that gives you B inverse and then C of that, and then you can factor it out. So this is already a nice what is transformation, because as I said, it transfer every matrix to the similar matrix. So this is just preserves the addition and scalar multiplication, and then it's just one-to-one or onto that's isomorphism. Okay, so for me it's easier to show this is one-to-one. Why this is one-to-one? I can just go by kernel, or I can just say, okay, this is going to be number one, so transformation of a sub 1 equals the transformation of a sub 2. So this is really what we can do, right? So that's the definition of this transformation, to transform A1 to B inverse A1B. And this is the transformation definition to do for A2 the same thing. So that's just writing the transformation definition from the original problem, and then that's just simply if you multiply left multiply by a b, and then right multiply by a b inverse. So then that's just simply say A1 equals A2, and that's just really means is one-to-one. So means is one-to-one, so it's isomorphism. Is there any question about this part? And again, to complete my discussion, I have had one question. Is that fine to move on? Guys, anyone is writing anything? Can I move on? Yes? Okay. So I have had something else over here, which I had to erase because of the space. So what was it? Question that I erased it because I will post this when I want to be complete, was if you have the diagonalizable start point of the matrix is just set of diagonal matrices. So this is diagonalizable. And then do you think the transformation of this by whatever is defined to be by this is still diagonalizable? Any idea? If you start with the diagonalizable matrix, whether the transformation is going to be diagonalizable by the way that is defined? Yes, no? Any idea?
I would like to say yes.
It seems yes, because of the way that this similarity, we like it, and it's just because it's just really follow the definition. But we can just really write down however we say, right? So we say D is diagonalizable. So sorry, A is diagonalizable. What does it mean? That means you can just write D as this form, or A as Q inverse, or D as Q inverse A Q. So this means the A is diagonalizable, okay? So, or the other way, as I said, so, or you can just say A is Q, D, Q inverse, because A is diagonalizable. And then all I need to do right is just follow definition for I, which was B inverse AB, and replace A by whatever is just the diagonal matrix. So it's just really this whole thing replaced by my what is it, A, because it is diagonalizable, and then that is really one left invertible matrix that I need, and then the other one is right. Is that fine to write it like this, or I need to add one more step? Let me add one more step. Okay, so what I've done is I have separate this piece, kept the D right here, then I have this one. So this is really the same as B inverse Q on left D. So that's just based on the inverse has to be reverse and inverse on top, right? That's just the property. When you inverse the product, is just reverse the order. So that's fine, right? Is it fine from here to here? And that is just really what the diagonal matrix I need, right? So the diagonal matrix that I need for this case, so diagonal matrix that I need for this case is just going to be B inverse Q inverse whatever is my transformation, and then B inverse Q. It's just really nice way of writing the transformation. And again, the transformation is one of the most important transformation here because of the similarity. The transformation, because it keeps all of my eigenvalues, right? So they are, if whatever is your eigenvalues of A, right over here is just going to be the same as the eigenvalues of the similar matrices. So then the diagonal matrix, as you see, they are connected. So this is just really, they are connected. Is there any question here? Is there any question here? This is about 9. As I said, I have a very short introduction to my new chapter just to save time, but you don't have to do anything today because the next week is just the spring break. We don't have any class next week, and it's these 2 days you will be busy with your, with your test. So that's just really goes to the following week when we come back from the spring. Okay, so when we come back from spring break, we will continue this one. It's just really a short introduction. So according to my schedule and what you've seen from the beginning of the semester, I said I start from chapter 5, and then I'll do 2 sections of chapter 7, and then I will come back to the chapter 5. So then that's just really the plan from the beginning of the semester. Why? Because this chapter 7 is really similar discussion that we have had by diagonalizable, and then if it is possible to make it diagonal, if it is not, what's the next plan? And then if you remember from the previous course, we have had the next plan. When we haven't had enough eigenvectors, we could build the new one, right? So then we have had W names for that, and then we could solve the system of equation. That building the next level or adding some eigenvectors is right here. So the idea, so maybe you have used it to just solve your system of equations. If you haven't had enough eigenvectors, you just had 1, you needed to make 2, so you just start to make those W1s. And but you didn't know why this idea is like that, why that equation gives you the new eigenvectors. But here we will learn that's what we call generalized eigenvector. Okay, so that's what plan was the in previous one. I mean, extend the eigenvectors if you haven't had enough is just really what we have it in chapter 7. So chapter 7 is not really the entire chapter 7, is partially 7.1, partially 7.2. So it means you can't go back to the book and study from the book. Is really how much I cover here. So, and that would be enough for you to do your homework, to do the test on this chapter. Okay, so this is not part of your test, and is that all of the assignments for this part is going to be after your spring break. Okay, but that's just really to start to give you the short introduction. Are you ready? Okay, so I just recall you one more time what we have had at the beginning of chapter 5. So the question on chapter 5 is, it was just if there exists any basis that we can just have the matrix transformation to be diagonal matrix. And then we just said, yes, there exists. That's just a set of eigenvectors. So that was just to answer the second question. Yes, how we can find it? We just get the eigenvalues. We just get corresponding eigenvectors. We put it in a set if we have enough. And that would be just the basis that the corresponding matrix is going to be diagonal. Okay. And then the question was, okay, if not, so if not, what's just the next plan? So if it is not, what is the next plan? So what is the next best of the matrix transformation that we can have? And that's just what we call Jordan Canonical Form. Okay. So it has a nice name, and it is just really same process that we have done by now. So that's why it's connected. That's why I just covered it right after chapter section 5.2. If I just translate whatever I wrote on top in version of what we call matrices on what we've seen it in previous course. So it says, if you have had the first question was, there exists a basis such that the matrix transformation is diagonal. So here there exists a Q such that the D can be written in this one. So that's just writing the matrix version. So if yes, what is that Q? So that's the same thing that we have done with the previous problem. So that's just really find the eigenvalues, find the eigenvectors, and then Q is just the matrix which the columns are eigenvectors. And then what's the next best if you couldn't just get enough vectors? And that's just an example, very simple example of 5.2. So section 5.2, problem number 2, part F. So there is the matrix which we just get the determinant, and we find the lambdas is repeated, right? So the lambda equals 1 is repeated, and then lambda equals 3 is just really once. So since lambda equals 1 is repeated, we expect to get, I mean, we hope actually to get 2 free variables, but we get 1 free variable, and we get only 1 eigenvector. Okay, so that's a problem. The multiplicity was 2, but we got only 1 eigenvector. We got only one free variable. Okay, so that's obviously is not diagonalizable. I don't have enough vectors to make my column of Q. I don't have enough vectors to make the basis that I need to, right? So because it's just really 1 free variable, but multiplicity was 2. So this says, okay, so that means this is too small. I need 1 more dimension of the eigenspace is just 1, because the free variable is 1, but the multiplicity is 2. So that is not diagonalizable. But what can I do? The next strategy is just go to the second, that's just really, do the second linear independence vector. So that's what we call generalized. So what do we call generalized eigenvector? The only thing is we want to be close enough to what we call eigenvector. So to be close enough what we call eigenvector, because eigenvector is just the solution to A minus lambda I. Eigenvector is solution to the A minus lambda I. So what is the closest way of defining what we call eigenvector or generalized eigenvector? Is just really go to the next power, and that's it. So if you have a matrix of n by n, and then you are looking for the eigenvectors, so the generalized eigenvectors is not A minus lambda I equals 0 or the null space of that, because I don't get enough from that. I just make it to the next power. So if it is first power, then I go to the second power, then it didn't work, I go to the third power. So then we will practice how many more we can go. So it's just, we have to continue that A minus lambda I to the next power if you didn't get enough vectors, okay? And this is just what you've seen it in previous course when you were trying to do the system of equations by using the eigenvectors, okay? In this P, again, for now, we have no idea how many is just going to be. Is it the second power that that's enough to get the enough eigenvalues, or is just the more power. So that's just really what we will practice. But what we know is, if that power is 1, if that power is 1, it's really the regular eigenvector, right? Generalize means you just go to the more power, but if the power is 1, it's just really regular eigenvector. So, and exactly same definition of matrices, you can just replace this A by matrix transformation, and that gives you linear transformation of this definition. So linear transformation version of this definition is just replace that A by matrix transformation. So if I do not have enough eigenvectors, what's the next plan? If I get 1, but I'm supposed to get 2, what's the next plan? Just change the power of A minus lambda I. That gives you the generalized eigenvectors, and that would be really, for this example, at least for this example, which lambda equals 1, haven't had enough, so I just go to the second power. So it means I raise it twice, so I multiply it by itself, and then I get the null space corresponding by this second power, and this time I will get 2 free variables, and perfect. That's what I really need, because the multiplicity of the lambda was 2. I just need to get 2 eigenvectors. By second power of A minus lambda I will get 2 free variables. So then two eigenvectors. So this one is repeated. I have had it. If I go back to the top, so I will go back to the top, and I have had that first one. This is the regular one. This is that what I got from the first power. So the regular one that I got from the first power naturally is coming again. This is always coming again, and then I got one more time, which that's perfect. So then I have 2 of them. So the original one that you got from the first power is listed always in when you just raise it to the second power, and then that's just really what you need, right? So multiplicity of 2 eigenvectors, and then you are done. Okay. And it wasn't really surprising to see the eigenvectors, as I said, as a regular eigenvector again. One more time here. Then the other lambda equals 3, because I haven't had the computation for 1. There was 2 eigenvectors of lambda equals 3 and 1. So this is for lambda equals 3. It gives you 1. That's enough. 1, 2, 3. So I just need to get 3 eigenvectors. And that's just what we call generalized eigenvectors. So that's the basis with the generalized eigenvectors. So that was the regular one. That was the regular one. So these 2 are regular. This is just the extra one. This is just the extra one. Does it matter which order do we put? Again, it's just really what you want to put in diagonal matrix. It does matter. Okay. So this is just what is it? The regular. I put it in the regular one is the first one. This is the regular one, and then this is the next one. So what does it change? What does it change is really the form of when you get the diagonal matrix. Okay. So your diagonal matrix looks a little bit different. So this is 1 and 1. This is 1 and 1 because you wrote this 2 for the lambda equals 1. And that is just for lambda equals 3, right? So this is for lambda equals 3 because your last one was lambda equals 3. Okay, so then your last column is lambda equals 3. But the way that you see, it looks like always like this. So it's not completely diagonal matrix. You do have always some ones on top, which is just upper triangle matrix, and that's what we call Jordan Canonical Form. So Jordan Canonical Form is not exactly diagonal, but it looks like diagonal matrix. If I just want to show you the more generalized one, you see, so you have your all eigenvalues sitting on the diagonal, but you do have always 1 on top. That's just what we call Jordan block. So the way that I have cut it in this way, it was just really the number of block. I got 2 eigenvalues, so I have 2 block. So 2 Jordan block. And then this is just really one example. So this is just the diagonal, and this is 1 here. So this says this is not the usual one, this is generalized one. So again, in a way that we fill out the column, so this one is regular. Let me change the color. So this is the regular eigenvector when you put it in Q form. But when you have this one on top, then this one on top, this one on top, so means in the column these are going to be the generalized one. What happened for your matrix, as I said, on top of that diagonal entry you will get the 1 when you have the generalized version, if you have the more power, and then you will guess what's the power, right? So if you hear your power was a minus lambda I to the second, because your block is 2 by 2, so here your block is how many? 1 2 3 4 5, so it is 5 by 5. So probably for this one your a minus lambda I to the 5th power was just really what you get the enough eigenvectors, because you got 1 from the first power and then you need to get another 4. Okay, is there any question? So as we see, it's not completely a diagonal matrix. It is always 1 1 on top of my diagonal, so it's upper triangle matrix. And then based on how many of those eigenvectors you can get, so this is just going to be the blocks that you get. So if you have this many, so blocks can be different size because you might have different repetition. So you might get just lambda equals 1 with the multiplicity of 3, lambda equals 2, just multiplicity of the 1. So then if it is 1, it's just really smaller size. If it is multiplicity of 2, it has 2 by 2 size. So that's just the number of repetition or multiplicity gives you how big is this block. So this is just numbers. This says the 2, the lambda equals 2 has the multiplicity of 3, because I have 1 2 3 columns, but I just could have one of them in regular and then 2 of them must be by your generalized one. So 5 was repeated 2 times, and then I should get just 1 from the regular computation, and then the next one was from the generalized one, so I had to raise it to the second power. So this 7 was repeated 2 times, but I just could get 1 free variable once in my computation, and then the second one is coming from the second power. So 7 has just a repetition of 7. Sorry, I missed this one. So 7 has repetition of the 7, so I could just get 1 and 2 seems 1 and 2 free variables. The third one is just generalized one, and that's just really multiplicity of 1 because it has the block of size 1 times 1. Any question? This is the fun one. Okay, so this is a fun one, and that's just I will say is all computations. It doesn't have that much proven theorems. It's just all computations of the a minus lambda I. If it doesn't get enough, so you go to the second power. If it doesn't get enough, you go to the third power, but you know where to go because of the multiplicity. So because of the multiplicity, it says I have multiplicity of 3, I need 3 eigenvectors. So how do I get them? If the first power of a minus lambda I doesn't give me enough, I go to the next power. Any question? Is there any question? Is there any question? As you see, I'm going to stop here. Okay, so this is enough for today. If you don't have any question, I'm going to stop recording for today. Do you have any question about this concept?
No.
Okay. If you don't have any question about this concept, no? No one else? So, okay, let's just stop recording.